Today we're going to look at projections and vector components. You've already seen applications in which two vectors are added together to get a resultant vector. Today we're going to kind of take those apart, if you would, and decompose a vector into its the sum of the two vector components. So we're going to look at the two vectors in essence that make up that one. And we'll see a couple applications with this as well in the next video. Here is an application. We're not going to solve it, but here's what we're going to take a look at. One of the problems. We're going to consider a boat on this inclined ramp. And the force F due to gravity is the one going straight down here. And it has two component forces together that add up to that one. So W1 is this force of the gravity down the ramp, if you would. And then this W2 would be orthogonal to W1 going straight down here. So F1 is gravity, or F, excuse me, is gravity pulling the boat towards the center of the earth. And the other two, since there's a ramp here, the other two components make up that. So we're going to be able to decompose and find either one or both of those, but this W1 is the one we're looking for. Alright, just as we saw in that picture, F is equal to W1 plus W2. They are orthogonal vectors that add together to be that the components of F. Okay. Alright, some definitions to know. Let U and V be non-zero vectors. Moreover, let U equal W1 plus W2, where W1 is parallel to V and W2 is orthogonal to V. Now that sounds like a lot of oof, what are we talking about? Let's take a look at the picture down here. Okay. See if we can get back to that. Okay. So we've got U is a vector here, V is a vector here, and W1 and W2 will add up together to be U. So if I took W2 right here and placed it at the tail, if you would, of W1, it would go straight up here, and together they'd be the components of U. Okay. W1 is called the projection of U onto V, or the vector component of U along V, and is denoted W1 is equal to the projection of U onto V. That's how we say that. Okay, what do we really mean? Well, imagine, if you would, I had a little sun up here. Alright, and it should be moved over just a little bit more, and it's projecting straight down. It's lighting it up, and where would its shadow fall onto this line? Okay, so here's vector V, and it just goes out, 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 right? It stops here, but if we considered it going on and on and on, the light of this, the shadow, would project, if you would, or a shadow of vector U onto this one. And so that's what we're considering. W1 then is the component, vector component of U along V. In other words, it's along. It's parallel to V. It's just a scalar of V. It's just a little bit longer in this case. Sometimes it might actually be shorter. Okay. And the other thing to know, the W2 component, since W1 plus W2 add together to be U in this case, W2 is simply U minus W1. So once we find W1, W2 is a piece of cake. Alright, here again we've got another picture, this time with an obtuse angle, and I would be putting the sun up here, and I know it's red, yellow doesn't show up very good. This red sky in the morning, think of that, or red sky at night. Okay, we got the projection going down here. It goes right at the end of the vector, if you would, and projects it. So its shadow would be this vector right here. And really the sun could be up here, but we want it to go straight down here, making that 90-degree angle right here. Okay, so W1 plus W2 will add up again to this vector U. Alright, we're not talking about how to calculate it other than how to calculate W2 at this point in time. That comes in just a minute. Alright, so here we go. Find the vector component of U which is this vector right here, that is orthogonal to v, which is the vector 4, 3, given that w1, the projection of u, is u onto v, is 8, 6. Now if I drew this, oh, I got it right, good. Okay, so I'm going to use a different color here, and I'm not sure what color it is, but this is the one I'm, let me use, is that pink or peach? I don't know, I'll pick that one. So that vector actually comes to right there. That's almost impossible for me to see, so let's go pick a blue one. I can see that one. So the vector goes to right here. That's the vector right here. W1, you notice is the vector 8, 6. If I were to cast the shadow down from here, and of course that's perfectly orthogonal, but that would come through here, and you can see how this would be the component form, vector component form of the projection of u onto v, and that's what's going on there. Okay, so it says we want to find the vector component of u that is orthogonal given that this projection. In other words, I want to find what is w2. So w2 is this part, right? What am I going to have to add to that? And we could actually probably calculate that if we just count it over a little bit. But let's go ahead and do the math. I think I've got it on the next page. U is equal to W1 plus W2. That's the two components that add together to be that vector. And W1 is parallel to V. It lies on that same line, either going with it or away from it, just longer or shorter. And it follows that W2 is the component, vector component orthogonal to V. So W2 is equal to U minus W1. We had 5, 10 minus 8, 6, which gives us the vector 3, 4. Let's go back in our picture. Actually, we can go forward, I think. And you can see to get from here to there would be this vector W2 minus 3 units and up 4. It's a little better picture than the one I drew, but you can kind of see here would be the sun up here shining down and projecting onto here. So W1 is that whole piece, W2 is that piece. All right. This is the last part of this lesson, I think, and then we'll move on to the applications. Projections and vector components. If u and v are non-zero vectors, then the projection of u onto v is given by this formula. So we can practice this. The projection of u onto v is u dot v over the magnitude of v times v. Now remember, the dot product is a scalar, the magnitude or the norm is a scalar, and then we're just simply multiplying it by that vector. So maybe we could go ahead and take a look at that last problem again right here. So let's take a look. We had the vector 5, 10 was being projected onto 4, 3. So let's see that we actually do get 8, 6. Let's just see how that works. So we had vector 5, 10. And being projected, so that was u. V was 3, 4, I believe. Let me double check. 4, 3, excuse me. If we do this, let's go ahead and do this math now, this projection. We'd get the dot product. U dot v is 5 times 4 is 20, plus 10 times 3 is 30. Take 5 times 4 is 20, 10 times 3 is 30. We add those together, divided by the norm of v. So that's the square root of 4 squared plus 3 squared. So that's 16 plus 9, and that expression squared, and then times vector v, which is 4, 3. So this number out front is a scalar. It's actually telling us what scale we're going to multiply 4, 3 by. 20 plus 30 is obviously 50. Square root of 25 is 5. Squared is 25. So I get 50 divided by 25 is 2. And I get 4, 3, which is equal to my 0.86. So there's one example of computing the projection, knowing u and knowing vector v. Okay. The projection of u onto v can be written as a scalar multiple of a unit vector in the direction of v. And so this is going to be, we're just saying it's a scalar multiple times the unit vector. And you can see the unit vector part is right here. And so the scalar part is simply u dot v divided by the magnitude of v, which we did up there to a certain extent. Or in a shortcut way, based on what we did in the last section, we could write that as the magnitude of u, or the norm of u, times cosine theta. So this is a helpful tool that we're going to be looking at in a little bit. The scalar k is called the component of u in the direction of v. So that's the component of u in the direction of v. And we're going to be using that shortcut sometimes as well.